Hello, this is Richard Hammack's Calculus 1 course. We are in part 4 of the course on applications of derivatives. Today, in lecture 38b, we have our second installment of LHopitals Rule, a technique that applies derivatives to the problem of computing limits. Last time in lecture 38a, we saw how to use LHopitals Rule to evaluate limits with indeterminate forms 0 over 0, infinity over infinity, and 0 times infinity. Today we'll see that there are 4 other indeterminate forms: infinity minus infinity, 1 to the power of infinity, infinity to the power of 0, and 0 to the power of 0. To evaluate limits that have these 4 new indeterminate forms, we use LHopitals Rule. It reads as follows. If the limit as x approaches c of f of x over g of x has indeterminate form 0 over 0 or infinity over infinity, then the limit as x approaches c of f of x over g of x equals the limit as x approaches c of f prime of x over g prime of x. This has the potential of making limits much simpler because, as you know, often, not always, but often when you take a derivative of a function, it makes that function simpler. So if you had a complicated limit that looked like this one, that was of form 0 over 0 or infinity over infinity, then LHopitals Rule says it's equal to this limit where you've taken the derivative of the top and bottom, and those may be simpler expressions. Let's look at an example where just that thing happens. The limit as x approaches 0 of 1 minus cosine 3x over 8x squared. X is approaching 0, so the denominator 8x squared is certainly approaching 0. And what about the numerator? It's approaching 1 minus cosine 3 times 0, or 1 minus cosine of 0, which is 1 minus 1. The numerator is also approaching 0. So this limit has form 0 divided by 0. So this is a limit that LHopitals Rule could apply to. So let's use LHopitals Rule here. The LH means L'Hopital, so we have applied LHopitals Rule and going from here to here. So we've replaced this limit with limit as x goes to 0 of the derivative of 1 minus cosine 3x divided by the derivative of 8x squared. And with the derivative of 1 minus cosine 3x, with the minus cosine 3x we had to apply the chain rule there, so the derivative of cosine is minus sine times that negative is a positive sign. Plug in the 3x, multiply by the derivative of 3x. And of course the 1, its derivative was 0, so it doesn't even show up here. But we get the limit as x goes to 0 of sine 3x times 3 over 16x. And that's still a form 0 divided by 0, because the sine of 3 times x is approaching sine of 0, which is 0, and the 16x is, of course, approaching 16 times 0, which is 0. So to this, we would apply LHopitals Rule once again. And in so doing, we've boiled away this 8x squared to just a plain old 16 after differentiating twice. So the denominator is really simple. And what's happening to the numerator? Well, it's cosine 3x times 9. And x is approaching 0. So here you can just plug in the x equals 0 into the x there. You get cosine 0 is 1. And the limit is then cosine 0 times 9 over 16, which is 1 times 9 over 16. And that's 9/16. Second example. Limit as x goes to infinity. 5x cubed plus 3x squared plus 1, all divided by 8x cubed minus x. This is the limit as x goes to infinity of a rational function. And you will recall that you have several techniques from way back in chapter 2 for computing this limit. The simplest is that you would just look for the highest powers of x on top and bottom and pick off those coefficients 5 and 8, and you know that the answer is going to be 5/8. That's what this limit is going to equal. But I propose that we do it in a slightly different way. If we examine this limit, the numerator and the denominator are both approaching infinity because x is going to infinity. So it has form infinity divided by infinity. And we could apply L'Hopital's rule to that. So applying L'Hopital's rule gives us the limit as x goes to infinity of 15x squared plus 6x, that's the derivative of the numerator, divided by the derivative of the 8x cubed minus x, 24x squared minus 1. And that's still a form infinity over infinity. So we could apply L'Hopital's rule once again, and these derivatives are getting better and better. But we still have form infinity over infinity. So we would apply L'Hopital's rule once more to get the limit as x goes to infinity of 30 over 48, the 30 being the derivative of 30x plus 6 and the 48 being the derivative of 48x. So here is now a limit that's very easy to compute. It's just 30 over 48, which reduces to 5/8. So the answer is 5/8. And it's kind of nice to know that we knew ahead of time it was going to be 5/8. It's refreshing to know that we have several different ways of computing this limit, and they all give us the same answer.
Remember also in our previous lecture, we learned how to deal with limits of indeterminate form 0 times infinity. And here's a quick review example. Think of the limit as x goes to 0 of x times cotangent x. Here, x is approaching 0, but cotangent has a vertical asymptote at x equals 0, so it's going to infinity. So this limit has form 0 times infinity, which is another indeterminate form. L'Hopital's rule only applies to limits of indeterminate form 0 over 0 or infinity over infinity. But we learned last time how to convert this problem into one of those forms that L'Hopital's rule applies to. You're either going to bring the x down to the bottom as 1 over x, or the cotangent x down to the bottom as 1 over cotangent x, as its reciprocal. And you could do either way, but you want to choose the one that's going to result in the simplest derivative. So here, x has a really simple derivative, where if you brought it down to the bottom, 1 over x has a more complicated derivative. And that tells you maybe you should leave the x up at the top and bring the cotangent x down to the bottom as its reciprocal. Now, 1 over cotangent x is tangent x, so this limit is the limit as x goes to 0 of x over tangent x. Now it's the limit of a fraction, and the top x is approaching 0, and the bottom is approaching tangent 0, which is 0. So this limit is a form 0 over 0. So we've converted the problem to something that L'Hopital's rule applies to. Applying L'Hopital's rule, the derivative of x is 1, the derivative of tangent of x is secant squared, and this is a simple limit to evaluate. You can just use a limit law here, and you get 1 over secant squared 0, and that's equal to 1 over 1, or just 1. So we've seen now and recalled that we can evaluate limits of 3 indeterminate forms, 0 over 0, infinity over infinity, and 0 times infinity. But there are other indeterminate forms, and the purpose of today's lecture is to explore them. To explain the first of these, consider the limit as x goes to 0 of 1 over x minus the expression 1 over x minus 1. This is intentionally simple. You can see that before evaluating the limit, if you distribute the minus 1 into the parentheses, you get 1 over x minus 1 over x plus 1, and so the limit of that just equals 1. Twisting this slightly, think of the limit as x goes to 0 of 1 over x minus the expression 1 over x minus 5. For the same reason, this limit is equal to 5. But look at the form that these two limits have. As x goes to 0, the 1 over x is approaching infinity. And likewise, the 1 over x minus 1 is approaching infinity as well, as is the 1 over x minus 5. So each of these two limits has the form of infinity minus infinity. So you can see here that infinity minus infinity is an indeterminate form. By itself, infinity minus infinity makes no sense. You can't say what that equals, but you can see here that you have limits that have those two forms that exist in equal numbers, not necessarily the same number. Your knee-jerk reaction might be to say infinity minus infinity equals 0, but that's not the case in these limits. It could be all over the map. So infinity minus infinity is our first new indeterminate form. There's some others. To illustrate them, think of this limit. The limit is x goes to 0 of 2 to the x to the power of 1 over x. This is an intentionally simple limit because if you, before evaluating the limit, multiply the exponents, you get 2 to the power of 1, and the limit as x goes to 0 of that is equal to 2. Think also of the limit as x goes to 0 of 3 to the power of x to the power of 1 over x. For the same reason, this limit is equal to 3. But look at the forms that these two limits take. In each case, x is going to 0, so the base 2 to the x, or 3 to the x, is approaching a number to the power of 0, which is 1. But the exponent 1 over x is going to infinity as x goes to 0. So both of these limits have the form 1 to the power of infinity. So that's an indeterminate form. By itself, 1 to the power of infinity doesn't make any sense at all. You might think that it's going to be 1, because any number, 1 to any power is 1, but infinity is not a number. It turns out that 1 to the power of infinity is an indeterminate form. It doesn't make any sense by itself, but both of these limits have that form, and they equal different numbers. Playing around with this problem, or these two problems, let's change it so instead of x is approaching 0, x is approaching infinity. Look at the limit as x goes to infinity of 2 to the x to the power of 1 over x. For exactly the same reason that we had above, this limit is equal to 2, because it doesn't matter what x is. 2 to the x to the power of 1 over x equals 2 to the power of 1. The limit is 2. And replacing that base with 3, same result. Limit as x goes to infinity, 3 to the x to the power of 1 over x equals 3. So in both cases, the limit exists and it equals different numbers. But look at the structure that these limits have. X is going to infinity, so the base 2 to the x is approaching infinity as well, and the 3 to the x is approaching infinity. But the exponent 1 over x, in each case, as x goes to infinity, approaches 0. So these two limits have the form infinity to the power of 0. The base is going to infinity, the exponent is going to 0. So you can see here that infinity to the power of 0 is an indeterminate form. It doesn't make any sense by itself, but you can have limits that have that form, that are meaningful, and that exist, and equal different numbers. So these are 3 new indeterminate forms, but we're not quite done. I want you to think about this limit. The limit is x goes to 0 of x to the power of 0. Now as x approaches 0, it's a number, And any number, a non-zero number, to the power of 0 equals 1. So x to the power of 0 is equal to 1. So this limit equals 1. A very simple limit. But compare that to the limit, as x goes to infinity, of 2 to the minus x to the power of 1 over x. It's easy to see what this is because before taking the limit, just do a little algebra. The exponents multiply. Negative x times 1 over x is negative 1. So you're taking the limit as x goes to infinity of 2 to the power of minus 1. So that's the answer. It's 1/2. Look at the structure that these two limits have. In each case, the base is approaching 0. X is going to 0 here. And in the second limit, x is going to infinity. So 2 to the power of minus x is like 2 to the power of a minus a really big number. And that's a really small number. And the bigger and bigger x gets, the closer and closer 2 to the minus x gets to 0. So this base here is approaching 0. And that happens in both of these limits. But what about the exponent? Here, x is going to infinity, so 1 over x is getting closer and closer to 0. And in this problem, the exponent is already 0. So both of these limits have the form 0 to the power of 0. So that's our final indeterminate form. It doesn't make any sense by itself, but you can have limits that have that form, as these two do, and those limits may exist, and they're not necessarily going to equal 1, as we saw here. So on this page, we have our 4 new indeterminate forms, giving a total of 7 indeterminate forms. There's 0 over 0, infinity over infinity, and 0 times infinity that we introduced previously. And on this page, we have 4 more: infinity minus infinity, 1 to the power of infinity, 0 to the infinity to the power of 0, and 0 to the power of 0. So what we'll do today is we'll talk about how to handle limits of these indeterminate forms. It turns out that, like 0 times infinity, for these other 4 that don't have the forms that LHopitals Rule applies to, you can always apply some algebra. There's some tricks for doing that to get it into a form that LHopitals Rule applies to. So let's start by looking at the indeterminate form infinity minus infinity and think about how to handle that. So here I've reminded you of the limit that we had on the previous page that had form infinity minus infinity, and there's also this one. Here's a limit that has that same form. The limit is x goes to 0 of 1 over x minus 1 over e to the x minus 1. 1 over x is approaching infinity as x goes to 0. And what about this other term? The bottom is e to the power of x minus 1, and x is approaching 0, so e to the power of x is getting closer and closer to e to the power of 0, which is 1. So the denominator is getting closer and closer to 1 minus 1, or 0. So this reciprocal is getting bigger and bigger and bigger. So this limit has the form infinity minus infinity as well. And it's not obvious what it equals, or even if it exists, the way it was for these two that had form infinity minus infinity. So in general, you might have something that looks like the limit as x approaches c of f of x minus g of x, where both f of x and g of x are going to infinity. These would be limits of the form infinity minus infinity. And down at the bottom of the page, I'm going to give you an algebraic technique for solving these. But before doing so, I want to say a little bit about this form infinity minus infinity, because sometimes it's hard to visualize because these quantities are going to infinity, and you might think the answer has to be 0 because anything minus itself should be 0, right? Well, obviously not. because we're getting different numbers here. Here's a way to visualize this indeterminate form, infinity minus infinity. The limit as x goes to c of f of x minus g of x, as f and g both go to infinity. Think about two cars racing down the x-axis, racing towards infinity. And the car that's a little bit ahead is, let's say, f of x units from 0, the origin, and the other car is g of x units from 0. And f of x and g of x are just going to infinity, so these cars are racing to infinity. But imagine that as they get further and further and further away, as f of x and g of x get bigger and bigger and bigger, the distance between these cars starts to stabilize. Maybe this car is catching up but never quite reaching this car over here, and in the long term, it approaches a distance of 1 mile behind this other car. And so they're racing off to infinity about a mile apart, but the distance between them getting closer and closer and closer and closer to 1 mile. In that case, the limit the f of x minus g of x would be getting closer and closer and closer to 1 mile. And you would have a limit of f of x minus g of x equaling 1. So think of this indeterminate form, infinity minus infinity, that way, if it looks confusing. So having said that, I can give you the technique that's going to work for evaluating limits of form infinity minus infinity. And it's this. The strategy is, if, and the limit as x goes to c, f of x minus g of x has the form infinity minus infinity, try to combine the f and g into a single term and apply L'Hopital's rule. For example, if f and g are fractions, try combining those two fractions into a single fraction, and you'll get something to which you can apply L'Hopital's rule. Let's look at some examples.
So, as an example, let's take the limit we looked at on the previous page, this one right here. We said, what is the limit as x goes to 0, 1 over x minus 1 over e to the x minus 1? Question mark. Let's try to figure it out. And this time I'll work vertically rather than horizontally. The first thing we'll notice is that, as we noted on the previous page, this limit has form infinity minus infinity. As x goes to 0, the 1 over x and the 1 over e to the x minus 1, they both approach infinity. So our strategy that we outlined would be to combine this difference into a single term. And to do that, you might think about getting a common denominator and combining these two fractions. Let's try that. The common denominator would be x times e to the x minus 1. And so to the 1 over x, you'd want to multiply that by 1 in the form of e to the x minus 1 over itself. And to the 1 over e to the x minus 1, you'd want to multiply that by 1 in the form of x over x. And notice in so doing, you get your common denominator of x times e to the x minus 1, and you can combine these two fractions. There's your common denominator. On the numerator, you've got an e to the x minus 1 minus an x. So now we've taken this difference and converted it into a single expression. And in looking at this expression, notice that it has form 0 divided by 0, because as x approaches 0, our e to the x is approaching 1, then minus 1, minus 0. So that's 0 on the top. And on the bottom, we have a 0 times e to the power of 0 minus 1. That's 0 times 1 minus 1. So that's 0 on the bottom. So both numerator and denominator are approaching 0, so we've got form 0 divided by 0. So this is a limit that we could apply L'Hopital's rule to. So here we go. We've applied L'Hopital's rule here. We replace the expression here with its derivative, which is e to the x minus 1. On the denominator, down here, we had to put the derivative of x times e to the x minus 1. And there we had to use the product rule, 1 times e to the x minus 1 plus x times the derivative of e to the x minus 1. And simplifying that, we get this. And that's still form 0 divided by 0. Plugging in a 0 to the top, we'd get e to the 0 minus 1 is 0. And down here, e to the 0 minus 1 is 1 minus 1 plus 0 times e to the 0. That gives you 0 down there as well. So we have to apply L'Hopital's rule to this again, since we're still form 0 over 0. But take heart, because notice that we're actually getting down to a simpler expression than what we had up here. So let's apply L'Hopital's rule one more time. We hope one more time. The derivative of e to the x minus 1 becomes just e to the x. The derivative of this e to the x is e to the x. The derivative of the minus 1 is 0. And then for x times e to the x, we had to use the product rule. It's right here. But at this point, I don't think we're still getting a 0 on the bottom. Yeah, x is going to 0, so we'd have e to the 0 plus e to the 0. That's a 1 plus 1 plus a 0 times 1. So on the denominator here is a 1 plus 1. So we're at a point now where we can just plug in x equals 0. In other words, take the limit as x goes to 0 at the top, divided by the limit as x goes to 0 at the bottom. And you get e to the 0 over e to the 0 plus e to the 0 plus 0 times e to the 0. And that's going to give you 1 over 2. So this limit equals 1/2. It's like those two cars rushing down the road. One of them's that far from the origin. The other one's that far from the origin. As time goes on, the difference between them gives a distance of 1/2 mile apart. Here's another example. The limit as x goes to infinity of ln of 3x squared plus 1 minus 2 ln of x. Now, as x goes to infinity, we know that ln of x is getting bigger and bigger and bigger. So the 2 ln x is going to infinity. And certainly the ln of 3x squared plus 1 is going to infinity, because the 3x squared plus 1 is getting big even faster than the x is getting big. So we recognize this limit as the indeterminate form infinity minus infinity. And remember our strategy for doing limits of the form infinity minus infinity. We want to combine these two terms into a single term. Now, last time we got a common denominator. I don't think that's going to work this time, because these are logarithms. Let's look at this. Well, one thing we could do, this 2 times ln x, that 2 could come up as a power of x. So we get limit as x goes to infinity, ln of 3x squared plus 1 minus ln of x squared. And now we could use a logarithm property to combine this difference into ln of 3x squared plus 1 over x squared. Remember that logarithm property? Forget the limit for a minute. Just look at the combining these two logarithms into this one. And now we don't have a difference anymore. It's a single expression. And ln is continuous, so we could take this limit as x goes to infinity and move it inside the ln. So we get ln at the limit as x goes to infinity of 3x squared plus 1 over x squared. Now this limit here, forget about the ln for a minute. Just look at the limit inside the ln. It has form infinity over infinity. So we know we can use L'Hopital's rule to work out this limit inside the logarithm. So applying L'Hopital's rule gives us the limit as x goes to infinity of, on top, derivative of 3x squared plus 1, that's 6x. On the bottom, derivative of 2x. So we get that. And here the x's cancel. So we just get ln of 6 halves, or simply ln of 3. So there's our answer. The limit as x goes to infinity of ln of 3x squared plus 1 minus 2 ln of x equals ln of 3. So the past two examples have shown us how to compute limits of the form infinity minus infinity, and you should work some examples of this to test your skill.
Let's turn now to our last three remaining indeterminate forms: 1 to the power of infinity, infinity to the power of 0, and 0 to the power of 0. We saw examples of each of these earlier in today's lecture. We had these two limits of indeterminate form 1 to the power of infinity. These two had indeterminate form infinity to the power of 0. And these two had indeterminate form 0 to the power of 0. It turns out that there is one technique that applies to all three of these indeterminate forms. And I'll explain that technique down at the bottom of this page, but first, off to the side, a quick review of some necessary information that's pertinent to that technique. We're going to be using ln and e to the x in this technique. Remember that the graph of ln of x looks like this. Its x-intercept is at 1. In other words, ln of 1 equals 0. And also the limit as x approaches 0 from the right of ln of x equals minus infinity, as you can see here. Because it's a logarithm, ln has this wonderful property that ln of b to the power of a equals a times ln of b. Also, because ln is the inverse of e to the x, e raised to the power of ln of a quantity equals that quantity. So any expression is equal to e to the power of ln of that expression. So we'll need this information, or these ideas, in our technique, which I'll now describe. It's really more of a trick. Suppose the limit as x approaches c of f of x to the power of g of x has one of the indeterminate forms, 1 to the power of infinity, infinity to the power of 0, or 0 to the power of 0. Here's what you can do. The limit as x approaches c of f of x to the power of g of x, by the property given here, equals the limit as x approaches c of e to the power of ln of f of x to the power of g of x. So we've just replaced the f of x to the power of g of x with e to the power of ln of f of x to the power of g of x. That's what we did here. So these two limits are equal. Now the next thing we're going to do is look at this exponent. It's ln of f of x to the power of g of x. We can use this property to bring the g of x down in front of the ln. So we get the limit as x approaches c of e raised to the power of g of x times ln of f of x. If this limit has one of these three indeterminate forms, then when you get to this step right here, you will realize that this expression, g of x times ln of f of x, has one of the forms 0 times infinity or infinity times 0. So neglecting the e for just a second, you'll see that you have the limit as x approaches c of g of x times ln of f of x. That's an indeterminate form, 0 times infinity, or maybe infinity times 0, depending on g and f. And the thing is, we can handle that. We already know how to handle the indeterminate form 0 times infinity. We talked about that in the previous lecture. So this technique will allow you to work out limits of these three indeterminate forms. Let's look at some examples.
Here's our first example. Limit as x goes to infinity of the x root of x. That looks kind of crazy, but if you convert that radical to a power, we're looking at the limit as x goes to infinity of x to the power of 1 over x. So the base x is going to infinity, and the 1 over x is going to 0, because it's a reciprocal of a bigger and bigger number, so it's going to 0. So this limit has form infinity to the power of 0. So that's one of our indeterminate forms. I wonder what it's going to be equal to. Let's apply our trick. Remember, our trick was to take this f of x to the power of g of x, right there, the x to the power of 1 over x, and replace it with e to ln of itself. So in going from here to here, these are equal because e to the power of ln x to the 1 over x equals x to the 1 over x. And then the next thing that happens is, remember, with an ln property, this 1 over x comes down in front of the ln. So we have the limit as x goes to infinity of e raised to the power of 1 over x times ln of x. Now the next thing I'm going to do is, since e raised to a power is a continuous function, we can bring this limit as x goes to infinity up in front of the 1 over x ln of x. So there we go. E raised to the power of this limit. So just covering up that e for a second, we're looking at of course we can't forget about the e, but we can for just a second. We have the limit as x goes to infinity of 1 over x ln of x. And that's form 0 times infinity. As x goes to infinity, the 1 over x turns into 0, and the ln of x goes to infinity. So as I said on the previous slide, when you apply this trick, you're always going to get either 0 times infinity or infinity times 0, and there we got it. And this is something that we know how to do. We talked about that in the previous lecture on LHopitals Rule. We can bring down either the 1 over x or the ln x down to the bottom. And in this case, it's really simple, almost deceptively simple, because in a certain sense, this 1 over x, that x is already on the bottom. We can just multiply it through, and we get the limit as x goes to infinity of ln x over x. And if you look at this limit right here, it is form infinity over infinity. Both the ln of x and the x are going to infinity here. So we can apply LHopitals Rule to that. Now, don't forget about the little e down there. It's being raised to this power that we're going to apply LHopitals Rule to. And in applying LHopitals Rule, the derivative of ln of x is 1 over x. The derivative of x is 1. And we get e raised to the power of the limit as x goes to infinity of 1 over x divided by 1, which is just the limit as x goes to infinity of 1 over x. And the limit as x goes to infinity of 1 over x, well, that's 0. So we get e to the power of 0 over 1, which is e to the power of 0, and that's equal to 1. And there we go. It's kind of amazing that we could figure this out. But the limit as x goes to infinity of the x root of x equals 1. this number is getting closer and closer to 1, the bigger and bigger you make x. You might want to test that with a calculator. Take a really big number for x, like x equals 10,000, and do 10,000 to the power of 1 over 10,000, and you'll get a number that's really, really close to 1. It'll be, I don't know, like 0.999999997 or something like that. But in theory, as x goes to infinity, the x root of x approaches 1. And that's what the limit equals. Here's another example. The limit as x goes to 0 of 1 plus x to the power of 1 over x. And looking at this, it's a form 1 to the power of infinity. Because x is going to 0, so the 1 plus x is approaching 1, and the 1 over x is getting bigger and bigger and bigger. So we definitely have formed 1 to the power of infinity. And what we're going to do is apply our trick that we talked about. That's going to be our strategy for these last indeterminate forms. We just replace the 1 plus x to the power of 1 over x with e to ln of it. So we get limit as x goes to 0 of e raised to the power of ln of 1 plus x to the power of 1 over x. So you just took all of this little cloud here, and replaced it with e to the ln of that cloud. And those are equal. Now remember the way this works, we're next going to use an ln property to bring this 1 over x down in front of the ln. Good, there we go. And now let's bring this limit up to the top. E raised to a power is a continuous function, so we should be able to bring that limit up. And we get e raised to the power of the limit as x goes to 0, 1 over x, ln of 1 plus x. It's almost easy to forget that e, but it's right there, remember, and it's being raised to the value of this limit. So looking at this limit here, limit as x goes to 0 of 1 over x, ln of 1 plus x. Well, x is going to 0, so 1 over x is approaching infinity. And ln of 1 plus x is approaching ln of 1, which remember is equal to 0. So this limit has the form of infinity times 0. That's an indeterminate form. And we know to evaluate such an indeterminate form that we can convert that to either 0 over 0 or infinity over infinity. It's really simple in this case. Just multiply the x through. It's kind of like the last problem we looked at. And we get the e to the power of the limit as x goes to 0, ln of 1 plus x over x. And x is going to 0. So the bottom here is going to 0. And the top is turning into ln of 1 plus 0, or ln of 1, which is also 0. So this limit has form 0 divided by 0. So we can use L'Hopital's rule to work out this limit that e is being raised to the power of. And applying L'Hopital's rule, we have on the bottom the derivative of x is 1. The derivative of ln of 1 plus x, remember, is 1 over 1 plus x times the derivative of 1 plus x, which is the reciprocal of 1 plus x. So there was L'Hopital's rule. And, oh, look at this. X is going to 0. And if you put in a 0 right there, it's 1 over 1 plus 0. 1 over 1. So we're at a point now where we can just evaluate this limit. We get e raised to the power of 1 plus 1. That's e to the power of 1, and that's e. So there we go. The limit as x goes to 0 of 1 plus x to the power of 1 over x equals e. This really shouldn't be too surprising, because if you think way back to, it was the first couple of weeks of class when we first introduced the number e, remember how we defined it? We said it was going to be the value of this limit that we couldn't work out. We just call the value of this limit e, and that was the definition of e. So it really shouldn't be too surprising that this limit turned out to be equal to e. Our last example, the limit as x approaches 0 from the right of x to the power of x. That's a weird looking expression, x to the power of x. And I'm making x approach 0 from the right because, with exponents, there are all kinds of crazy problems when you have a negative base, like, a negative number to the power, like a -2 to the power of -2. You get some radicals that you can't work out there. So here, to make things work out nicely, or to make sense actually, x is approaching 0 from the right. The limit as x goes to 0 from the right of x to the power of x. Now that is definitely form 0 to the power of 0. Both x on the bottom and x on the top, they're approaching 0. So we can apply our trick to this indeterminate form. We replace x to the power of x with e to the ln of x to the power of x, since those are equal to each other. And then we're going to use an ln property to bring this x down in front of the ln. So there we go. And next, let's bring this limit up to the power there. So we get e raised to the power of limit as x goes to 0 from the right of x ln of x. And then looking at this limit here, just neglecting the e for a second, this limit has form 0 times infinity. The x is going to 0, and remember, as x goes to 0, ln of x approaches negative infinity. So for all intents and purposes, this is 0 times negative infinity, which we'll just say has form 0 times infinity. So that's a limit that L'Hopital's rule can be applied to. Well, actually, I take that back. Not yet. We can apply L'Hopital's rule to this because L'Hopital's rule only applies to forms 0 over 0 or infinity over infinity. But we know we can, our strategy for 0 times infinity is to bring either the x down to the bottom or the ln of x down to the bottom as its reciprocal. Let's take the x under the ln of x and switch it to its reciprocal. So these two are equal. But now we have e to the power of the limit as x goes to 0 from the right of ln of x divided by 1 over x. And x is going to 0. So the ln of x, it's approaching negative infinity, and the 1 over x is approaching positive infinity. So this limit has form infinity over infinity. So that limit right there, we can use L'Hopital's rule on. Bring the e down, don't forget about the e, and applying L'Hopital's rule to this limit, the derivative of ln of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. And then we can simplify that. That's e to the limit as x goes to infinity, it goes to 0 from the right of just negative x. So that's equal to e to the power of 0, which is 1. So the limit as x goes to 0 from the right of x to the power of x equals 1. And there we go. Before concluding, I do want to mention one thing, and I think I've said this a few times, but it bears repeating. Whenever you use L'Hopital's rule and you get a new expression, you should always try to simplify that expression, because if you look at this one, it's still form infinity over infinity, but you definitely wouldn't want to use L'Hopital's rule on that again, because that simplifies to just plain old minus x. So always try to simplify before you apply L'Hopital's rule, and you'll save yourself a lot of grief. That's it for today. We'll close with a summary of what we've learned in lectures 38A and B. We've seen that there are 7 indeterminate forms that limits can take, as listed here. And we've learned about LHopitals Rule, a technique that allows us to evaluate limits that have the first 2 indeterminate forms. For the other 5 indeterminate forms, we've learned algebraic techniques to convert the problem to something that we can apply LHopitals Rule to. And here's a summary. If your limit has form 0 over 0 or infinity over infinity, that's something that you can apply LHopitals Rule to immediately. If you have the indeterminate form 0 times infinity, write your limit as x approaches c of f of x times g of x in the equivalent form limit as x approaches c of f of x over the reciprocal of g of x. Or alternatively, you could bring the f of x down to the bottom as its reciprocal. And when you do that, you will have form 0 over 0 or infinity over infinity, and you can apply LHopitals Rule to that. If you have the indeterminate form infinity minus infinity, try to consolidate that limit, or what you're taking the limit of, into a single fraction and apply LHopitals Rule. And finally, for the remaining 3 indeterminate forms that have the powers, write the limit as x approaches c of f of x to the power of g of x in the equivalent form limit as x approaches c of e raised to the power of g of x times ln of f of x. And we saw in today's lecture that these 2 limits are equal. Once you've written it in this new form, you'll discover that the exponent, g of x times ln of f of x, has the form 0 times infinity, or maybe infinity times 0. Either way, you can handle that as stated above here for the form 0 times infinity. And that's it. It's important to get a lot of practice with this, but usually you get good at LHopitals Rule pretty quickly. The effort pays off. So that's it for today, and this is also the end of part 4 of the course, Applications of Derivatives. When we come back, our next lecture will be in part 5 of the course on integration. I'll see you then, and goodbye.